stronger its conjugate base, the more willing the base is to accept the H+, the weaker the acid will be, because the acid won't want to give off the H+, because that conjugate base wants to hold on to the H+. Okay? So it's a balance between Ka and Kb, between the weak acid and the conjugate base. One goes up, the other has to go down. Okay? Because they are a conjugate acid-base pair. They're related to each other. Okay? Okay, so that's kind of easy to remember, just remember now. So not only do you have to be able to convert the pH, pOH, hydronium ion concentration, hydroxide ion concentration, interconvert between those four quantities, also be able to interconvert between Ka and Kb, and hence also be able to determine pKa, or if requested, not sure when you need it, pKb. Because P always means minus log base 10. So pKa minus log base 10 Ka. Okay, so that's just a point on that. And this is basically just what I talked about in words, so let you read that over. But basically, as the weak acid gets stronger, the conjugate base has to get weaker, and vice versa. Now, here's an interesting point. What about if you have a reaction between a weak base and a weak acid, and say not involving just the water, but between themselves? How do you deal with this sort of equilibrium reaction? Well, it follows a similar sort of route. Okay? It turns out that if you look at now this reaction, the forward direction, HA plus B minus forms A minus and HB. This, okay? This reaction, equilibrium reaction here, consists of these two equilibrium reactions dealing with water. In other words, Ka, the weak acid HA, is written in this direction, okay? And if you take the reverse of the Ka expression reaction from the other acid, HB, you write in reverse, you would have this. In other words, HB, another weak acid plus water, reacting in reverse goes back to hydronium ion and B minus. So the equilibrium constant for that is 1 over Ka of the HB. Equilibrium constant for this is Ka. So if you want to look at the reaction equilibrium of any two weak acids of themselves, what's the point of equilibrium? It's a ratio Ka, the weak acid HA over HB. And the stronger it is acting like, the stronger HA is as an acid, the more of these products you form. The stronger the other weak acid is, the more of these products you form. Okay? So just an application of how we manipulate equilibria to calculate equilibrium constants, in this case for acid-base reactions. Okay. Okay, so that's, I want to get into the next point because it's pretty straightforward because I'm a little short of time. And should be able to get through it. It's one of these topics that a lot of students say, oh, heck with it, this is confusing, I'm not going to figure it out because it's complicated. Yeah, it looks complicated, but it's actually pretty simple. So please listen in because these are like easy points for quizzes and exams. And that's basically how do salts change the pH of water? You might think, well, salt, it's neutral, it doesn't affect pH at all. Answer, that is wrong. Only some salts are going to leave the solution neutral in pH. Other salts will change the pH, sometimes acidic, sometimes make it basic. How do you know what's going to happen? Okay, let's look at some examples here. For cations, if the salt has the ammonium ion, or we're not going to really delve into this so much, but hydrated transition metals, don't worry about that so much, but it's another example. Well, they could act like weak acids. But do recognize at least the ammonium ion is a weak acid, and you could have salts with the ammonium ion. Ammonium nitrate, for example, ammonium chloride. Okay, these are salts, and yet when they have the cation ammonium ion, that ammonium ion is a weak acid, you put it in water, what happens? It dissociates, you have the ammonium ion and the chloride ion, okay? The ammonium ion is a weak acid, so it's going to make the solution acidic. The chloride ion, it's not going to have any effect, it's a spectator ion, okay? And the same for these hydrated cations. Again, for this course, I'm not going to delve into it, I just say it as additional information. Okay, So, now, what are the salts affect? So, first of all, salts that have ammonium ion is the cation. That's what you're responsible for. You should recognize that the ammonium ion is a weak acid. So, a salt with the ammonium ion is the cation makes the solution acidic. Okay? Because of the ammonium ion. Now, which anions is going to make the solution basic? Well, those anions that are conjugate base of a weak acid are going to make the solution somewhat basic. Why? Because that anion in water goes to the weak acid plus hydroxide, and the hydroxide is what making that solution as basic. Okay? When you form this HA, this conjugate acid, when that weak acid, when that acid, I should say, is a weak acid, what's the thing about weak acid? They don't dissociate very much. So if you have this conjugate base here as an anion, okay, in reaction with water forms a weak acid, the position of equilibrium is going to be towards the formation of these products, and the solution will become basic. If the anion is a conjugate base of a strong acid, like HCl. So say you had sodium chloride. Okay, sodium is a spectator ion. The chloride ion in water, according to this equation, Cl minus plus water goes to HCl plus OH minus. What happens to HCl? Well, it's a strong acid. It just dissociates again. The reaction doesn't take place because that strong acid doesn't form. It dissociates. But if you have acetate ion, for example, in water, you form the acetic acid in OH minus. The acetic acid is a weak acid, so some of that acetic acid will form, and in the process, you will form some hydroxide. Okay? So, the bottom line is that when the anion is a conjugate base of a weak acid, not a strong acid, a weak acid, it would basically have these reactions taking place, which forms hydroxide. Okay? Okay. So, prove it that we can do a calculation.